gonna be doing Codeforces Round 960. It's a Div 2, so I'm hoping I can probably get like A through D. No guarantees though. But yeah, see what we do. Okay, array says M. Alice starts first. MX. Oh, okay. So we get the next one. The first player who cannot operate will lose. So AI is So we want to take the running max. This should always be the case. So if there's only one max, we can take it, and that clears it. The only case when it shouldn't work is if there's an even number of the max. And then basically there's an even number of every element. If that's the case, then let's see, how large is it? Each A goes from 1 to N. Okay. Because otherwise Alice can just pick the max, otherwise pick the second max, and so on and so forth. So if there's any odd occurring element, then we're good. But if everything is even, then it's impossible. Yes, no, yes. That should be good. Okay, array craft. So we're given an array B. We have prefix maximums and suffix maximums. Oh, we're talking about the index here, not the element. Now we have n, x, and y. Construct an array. 1 or negative 1. Maximum prefix position is x. Okay. And we only have to print 1. Oh, so it's like Cadaine's algorithm. So then if, let's see, if we want it to be x, then at position x it has to be a positive one, and everything after has to be net 0 or net negative. So the number after has to be a negative 1, then we can have a 1 or a negative 1, and so on. And so, let's see. That should be straightforward. I think we can just proven that such an array always exists. So we can alternate ones and negative ones to get net 0 until we hit our desired position x, in which case we're going to have an extra 1. X is greater than y. Okay. So let's see. I'll just write it out. And I mean, it should be straightforward, but I just want to get it down. So imagine that we have x and we have y. They're both going to be 1. And we can set everything in between them as 1 as well. It's the maximum prefix. And then everything else can just alternate 1s and negative 1s. And so on. And that should work, I think. So we'll go from y up to x. And then everything else we're just going to alternate. So we're just going to multiply by negative 1 each time, and then we're going to go downwards as well. And then we're going to print the answer. Okay, 1, 1, 1, negative 1. Okay, let's see. Does that work? So 6 and 5. So x, the best prefix is 6. No, it's fine. Okay, so that's correct, and the maximum suffix is 1. That's correct as well. So for 1 to 5, we just have all 1s. Yeah, okay, that should be it. And so just as a proof that that works, we're always, if everything between x and y is 1s, we're always going to want to take the full thing. And if everything after that alternates, then we never have anything to gain from it. Yeah, that should be it. Okay. We define the maximum appearing duplicate as the largest number that appears at least twice. Specifically, there's no number that appears twice in 0. Okay. Initially, the sum is 0. And we'll repeat the following operation. Okay, denote the sum, let B be an array. So the maximum appearing duplicate of all prefixes, and replace the array with that. Okay, and that passed. Find the value of the sum after the process. So oh, and so we take the sum across all versions of the array, because eventually it'll just be 0, so it'll be the same no matter what. But we want, okay. What I'm wondering is if we can just simulate this. Like if it's gonna get cut in half every time or something like that. So So if a number appears more than 2 times, then if a number appears more than 2 times, it's going to show up twice in the resulting array. But if it shows up like 4 times, for example, then it's going to be kind of redundant. So yeah, I'm tempted to just write like a simulation solution, but I'm not sure if that's what they want. Okay, so zeros we don't care about. Like we're not gonna add zeros into the array at all, because that won't change the value by anything. But what we can do is if we have an array, we can look at the second occurrence of a number, and that's when it's going to update. And from that second occurrence onwards, the value is going to be that, until we find the second occurrence of something greater. And after we run this, the number is, or the array is already going to be sorted in increasing order. Okay, so no matter what, we should just solve it first. Okay, so how large are the numbers? Okay, the numbers only go up to n, so we'll update the max. And we'll just run a debugger and see what it looks like before and after. So it goes from 1 to 0, okay. 2, 2, 3, 0, 2, 2. Okay, so yeah, like I thought, it's going to be in increasing order. And now, so what's gonna happen if we run this multiple times? So I guess conveniently, since I wrote it like this, I can like write it as a loop, but right, okay, so it's gonna like almost staircase itself. So Like if we had this number 2, so array 2, 1, 1, 2. Well, we don't care about the initial version, but after we've solved the first iteration, we have an ascending list of numbers. And if some number appears x times, then the total number of occurrences will be x plus x minus 1 plus x minus 2, so it's a staircase from 1 to x. So you can just write that as x times x plus 1 over 2. And so I'm just going to check that with like a larger number. Say if our array is like so that appears once. Oh, actually, okay. Never mind. So it's gonna look like this. And every time, it's just gonna, it's gonna shift to the left, or to the right. And we just cut off the last number. Okay, so what we can do then is we can take the total sum, and we can just repeatedly pop back and update the sum. So, okay. Forgot to remove the debug loop. So 1 is still wrong. So let's see what A looks like after. So 223 turns to 022. And let me bring this back and just see what happens. So that should be 1, 2, 3, 4, 5, 6, 7, 8, 9. Really? Okay. Oh, that makes sense. Okay. So the number of occurrences here, this turns into 3 occurrences, which turns to 2 to 1. And then the 1 just turns to 0. So okay, I can kind of see the pattern, but it's hard to see how, like how you can write this as a formula. So, if we have, x occurrences, it's going to turn to x minus 1 occurrences, but if it's already at 1 occurrence, it's going to get cut to 0 by the next move. We could technically simulate multiple moves, like just a constant factor. And what that's going to do is it's going to then every number is going to appear some number x times. And after that's the case, then we do the staircase thing. So we can simulate this a constant number of times. Right, so the staircase pattern is going to happen, but it's only after we get rid of those one occurring elements, which should go away if we simulate 2 moves. 113, 940, okay. And I mean, we could increase this just to be safe, but like we do like 10 moves, which is still a constant factor, but we could do like, let's see. Do something like this. I mean, I don't really feel like writing that out, but okay, that turns to 1, 2, 2. Right, okay. I'm gonna simulate that. There's an N by N grid. The first AI cells are black and the other cells are white. Alright, it passed, nice. Okay, so we're given an n by n grid, but n is way too large to iterate over, so we're just told about each row as a number. That tells us how many of the first cells are black. Then you can do the following any number of times. Die a 2x2 subgrid white, otherwise die a whole row. Find the minimum number of operations to die all cells white. So it's at most n, because we can just die every row. And then I'm gonna just get the input first. Okay, then once we have that, so our initial answer is just going to be n, because we can die every single row using this second operation here. But then we want to see if we can do better by dying entire but then if the rows are long, we're not going to want to use this type 1 operation, because if we had like, you know, black, 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 and whites, okay, if we had something like this, we could die this subgrid here, this 2x2, and then we could die this 2x2 as well. And so we're using 2 operations, which is the same as if we just died both rows individually. But if they look like this, then you can save a move. So if both of these are basically less than or equal to But if you have something like this, then trying to die the individual 2x2s is not going to be beneficial. So if we're going to be dying an entire row, then we're never going to want to use a 2x2 move that involves that row. Because we might as well just start at a row lower. So it's kind of pointless. And then that means that basically for every row we have two options. Either we die the entire row, or we die everything using 2x2 moves. Which means those 2x2 moves are going to tile as much area as possible. If we do that, then again, using the rules from before, we're only going to want to do that if the value is less than or equal to 4. I'm going to look at the test cases because there might be like some weird pattern here. So if it's 2, 4, 4, we can do that in 4 moves, right? 3, okay. Oh, I see. Okay. So when we apply these operations, I think we can greedily pick starting from the end. But when we do that, so that's important because with that test case we have we have 2 and then 4, 4, 2. And then 2. So let's see. Normally you could just pick, you know, 1 row, 2, 3, 4, and then you're done. But you could be smart about it. You can pick this, this, and this. If an array has less than or equal to 2 elements, let's just greedily pick the 2x2 move. And if the row and the row that come after it have if the current row has 3 or more, then it's not really going to make a difference because we could either pick this or we could pick something like this. But it's going to be the same number of moves and we don't really accomplish much. So this might just be a greedy problem. I don't think we have to do DP. So look at the other cases. 3, 2, and 1. With this, following the greedy rules, it has 3 or more, so we just pick this. this has 2 or less, 2 or fewer, so we pick this. That's about it. And now, so that's 2 moves. Let's see. Yep. Okay, 0, 1, that's obvious. 3, 1. So we have 3 and 1. We have to do 2. Pick this, and then we pick basically this, even though there's nothing after. So 2 moves. 3, 1, or 3. That is just 3 moves, yes. 0, 2, 2, 2. So we'll just say 2, 2, 2. Greedily pick the box, and same for the one below it. That's 2 moves. And I mean, it's probably not necessary to manually do all these cases, but I don't want to miss something. So 1, 3. I think the hard part is just going to be the logic of tracking which parts of the next row we've removed, because it might not directly be... Yeah, it might not be from the beginning. Okay, so without looking at the answers, following the rules, we can do this. That leaves us with 1 left, so we'll pick the box. We'll pick the box again. We'll pick this, so it's 4. Yes. Okay. 2, 2, 5. 2, 3, 4. And 2, 4. Alright, now let's see. So we'll greedily pick the box. We'll cross the whole row. We'll greedily pick the box again. We're only left with 1 element, so we'll pick this box. That reduces the next row by 2, so we have 2. We'll pick this. And then we pick this. So 1, 2, 3, 4, 5, 6, and that's correct. Okay. So now I just gotta implement it, which is gonna be a bit of a pain, but so we can use booleans because we're only ever going to be drawing a box completely from the left or shifted by 2, so we could just have a boolean here. Call it box 1 and box 2. So if this is going to be the case when the row's already been cleared and we don't have to do anything. So if it's 2 or fewer, and actually we'll say that if either if it's already 0 or we have the case where it's less than or equal to 2 but we've already filled the box from previously. We want to clear these booleans. Then we just skip it. The other case is, and these booleans, these are only ever going to, only one of them at a time is going to be active. If So if we have 2 or fewer, and, well, either we have 2 or fewer, or it's between 3 to 4, but we've already filled the previous box. So, or it's less than or equal to 4, and we filled box 2. Then, again, we'll clear the booleans. But in this case, we'll actually fill box 1. And this costs a move. I'm just writing continues, I just want to handle all these separately. And so, this is the case when we fill the box. Then the other case is, what does that leave us with? So, either the row is going to be larger than 2. Either it's larger than 4, or it's larger than 2 and the box wasn't filled. Either way. A lot of kind of annoying casework here, but so that's when we fill the box. If that condition isn't satisfied, we'll have the case where A is either 3 or 4, but we fill the first box, which means we're going to fill the second box. Okay, so this is the case when we fill the first box, this is the case where we fill the second box. Then we want the case where we do neither. Oh yeah, and the top one is just when we don't have to do anything. And then after that is the case where we just cross out the row, and that's it. And let's see if it's correct. Zero, 3, 2, 1, 2, 2, 3, 2, 4, 6. See if there's any edge cases here. And the moves won't overflow because it's only at most 10. Okay, this is easy and hard. So let's see what the easy version is first. Oh, nice. Okay. I wasn't sure if I was gonna get that. Alright. I'm surprised that was greedy. I read it and I assumed that because it was problem D, it was probably gonna be like DP or something like that. Okay. So catch them all. This is the easy version. Limit is the number of queries. Oh, and it's interactive. Okay. So you have a tree. There's a hidden mole. You can pick and make an inquiry. Or return 1 when the mole is in subtree X. Okay. If the judge returns 0, if the judge returns 0 and the mole is not in root node 1, it will move to the parent. Okay. Huh, always the parent. Okay. Use at most 300 operations. So So if the height of the tree was less than 300, then we could just pick like a random node. And I mean, if we get it right, then we get it right. Like if we pick a leaf. And wait, actually, okay, we are told the structure of the tree. And which one is the root? Okay, node 1 is the root. So we could pick a random leaf. I mean, if we're right, then, you know, we're lucky and we just print that. But otherwise, the mole is just gonna climb the tree and we'll just keep on getting wrong guesses using 300 queries until we know that it's reached the top no matter what, because we iterate with the number of times being the height, and afterwards we just guess that. So that's something we could do. Otherwise, okay, so we have 300 queries. What about the hard version? 160. Okay, that doesn't sound that much worse, unless I'm just clueless here. And the interactor is not adaptive. Okay. So we just need to come up with a strategy. So, and there's only 5,000 nodes. Actually, let's just show an example. So say that the mole is like, I don't know, here or something. So obviously if we guess this, if we guess the root, it's always going to be correct. So it's kind of redundant to ask that. We don't really need to ask it, the root. But we can pick like, and I'll draw out the subtree a little more. What we can do is we can ask children of the root. So these smaller subtrees here. If we ask it this here, and it says no, then we know that this entire subtree is not gonna contain the mole. And so we can just like cut out the entire subtree completely. And then the other case, okay, so what happens if we get it wrong is that it's then going to, the mole is going to go up no matter what. And so that means that if the mole was here, here, or here, well then it's no longer going to be there, which means that we can trim every leaf. And now we basically just have a simplified version of the tree, where the mole could equally likely be in any of these places, and we just don't know. And I mean, obviously we drew the X here, but like, imagine we didn't know that. Then what we could do is, assuming we had more subtrees, we could just continue picking a subtree and keep on doing that. And so, I think what's gonna happen here is that if we pick some strategy like, either like pick the subtree with like the deepest roots, or pick the subtree with the most nodes or something like that, what's gonna happen is that we're gonna keep on cutting the tree in half. And so what's interesting is that I think we actually intentionally want to keep getting things wrong. Like we want to just keep on getting wrong answers, because by doing so we can just keep on cutting subtrees. And so imagine we had some consistent way of being wrong all the time. subtrees. Is this going to be square root n, because n could have like square root subtrees with square root elements each. But then, okay, we're given 5,000. Oh, it's only 70. Okay. Because I think the absolute worst case that we could have, the best case is a tree where just the maximum height is just like 300 or less, or like 160 or less. In which case we just, keep on getting wrong answers, make it reach the root, and then print that. The worst case is when we're gonna have like a root, and then a bunch of subtrees that are just like chains. And that's gonna be bad. And so, first of all, if we have a subtree, and I mean we could use this for the case of 300, but I'll try to solve for the 160 version because that would be way more points, as in E1 and E2. If the height of a subtree is less than or equal to 160, then we don't even have to like query it. We can just basically just keep on guessing other subtrees, and eventually that one, if the mole was in there, it'll reach the root, basically. And so what that means is that all, I guess, valid or candidate subtrees have more than 160 nodes. And so the number max number is 5,000 over 160. What is that? Oh, so that's only like 30. And so we only have 30 subtrees that we really care about here. And so we can just figure out which subtrees we care about, like which subtrees are considered important. And then if a subtree is important, we'll add it to our list. Unimportant subtrees we never query, because we know that at the end of our queries, if the mole was there, it'll be at the root, and we can just answer the root if we don't find anything. Then we'll go through all the important subtrees, and we'll query the root of each. If it returns a 0, then we cut it out, and we don't even care about it. Like we could just pretend that subtree doesn't even exist. If it does return a 1, I think this is where you start binary searching. And so what you can do, that's when it gets hard, I guess. So if we query this, child subtree, and it returns yes, then every other subtree is going to be removed. So it's kind of the reverse thinking. And so we get rid of everything else, And we've essentially just square rooted the size of the tree, in theory. Oh, but then that could be really large, which makes it hard. So yeah, I think the difficult part of this problem is what happens once you figure out which subtree it's in, if it's a large subtree. Because it might not actually be a literal chain, it might be something else. Is this okay? It seems like what we're going to want to do then, unless I'm thinking of this wrong, is that we're going to want to, because of all these edge cases where we're like trimming really small subtrees and just constantly recomputing large subtrees, we're going to want something where we consider all of the nodes whose distance from the root are greater than 160. So nodes where we'll actually want to catch them all. And we want, if we guess a subtree and it returns no, then what we've done is we've eliminated like a ton of different candidates. And so by doing that, then theoretically, we could cut down the number of candidate nodes in half every time. And we don't actually have to cut out candidate nodes, we could just cut out, like, nodes in general. Like, we try to pick the subtree that cuts the tree in half, roughly. But then that seems like a difficult problem because you have a tree, and it's a rooted tree. And you want to pick the subtree that has closest to half. That sounds like centroids or something. So, yeah, okay, okay, I think I'm on the right path here. The centroid is defined as the node that when the tree is rooted there, no other nodes have a subtree of size greater than n/2. So yeah, that's perfect. So we can find the centroid of a tree by starting at the root. Each step. Otherwise, move to the child with a subtree size that is more and repeat until you find a centroid. Okay. But how do you decompose it into? Because it's one thing to find one subtree or one centroid, but once we actually split those subtrees, we want to like basically centroid decompose them again. And so subgraphs at the centroid, producing log and layers of subgraphs. We learn it now. The only thing that I can think of that's going to make this really annoying is that technically for a rooted tree, we can query the centroid, and everything below that, if we treat that as the root, is going to be queried. And if it's no, then we can throw out that entire subtree, which cuts the number of nodes in half. But the problem is, if it's a yes, then there's the possibility that that the mole could climb out of that subtree again, which makes it really frustrating if you consider that detail. Whatever, I mean, I'll continue with this. What is this point? Xenia and tree. This is like a tutorial. I mean, I guess this is fun. Like, where is it? Because it could be considered a centroid when it has like a ton of subtrees below it, and then a small subtree above it. Because it thinks, oh, if you delete that centroid, you're going to be left with a bunch of subtrees, but you want something where you query a node and the number of nodes above it is roughly equal to the number of nodes below it. In other words, the size of the subtree is as close as possible to n over 2. In theory, this should be fine because what you can do is you can just, if you do some iteration and you find a subtree that matches this, like it comes within, you know, some constant factor of half the nodes, you can check this subtree and then either remove it or only focus on it and remove everything else. And then if you do like the whole like DFS recomputation, you're only doing it on size n over 2, which will then become n over 4 and n over 8 and so on. So the actual computation shouldn't be too hard. It's just, again, that case where you check a subtree, it misses, and the mole climbs out of the current subtree you're looking at, which means you have to expand the tree. kind of frustrating, but we asking ChatGPT. Close to n over 2. Is that... Bro, stop talking. The closest you can get... Well, I know you can do this for a non-rooted tree, but what about a rooted tree? I guess it's the same thing. What is it? How about we just pick the floor, and we'll get as close as possible to the floor. Okay. Finally implementing. Oh. I was like, wait, they tell us them all? Okay, so we get N. Okay, so we have that. We could compute like a parent array. That's probably useful there. Okay, so that sets all the parents. So then what we can do is we'll say that there's a total of n nodes, and while there are more than one nodes, then there are more than nodes. And I think what we're going to have to do is we're going to have to modify the adjacency list so that whenever we trim stuff, we just clear out the adjacency list for deleted nodes. And we just pretend they don't exist. I guess we'll do a map because it's not necessarily going to be contiguous. Okay, so that should be good. Now, we want to pick the subtree that's as close as possible to n over 2 without exceeding it. Call that nodes. So
yes, question mark x. Okay, if yes, remove all other nodes. much time is there? Oh, actually a lot of time. I know for a fact there's gonna be so much debugging here. Good thing I caught that. That's it. Alright, now will it seg faults? Wait, subtree sizes. Oh, what? Right. Forgot that my running script, it's asynchronous. Okay, so as to, let me try this. So in this example, let's say the null is at node 2. Okay. 1 and 2, and the null is here. And so it asks about 2, and we say yes. Return yes. Huh? Okay, it should know that there's only one. Right, so why would it ask for 2? Very best. Subtree sizes. The subtree size is not. No. Yeah, lots of debugging here. Zero is of size 2, 1 is of size 1. Oh, right, and it's 0 indexed. Okay, so it asked about 2. We said that 2, yes, it exists there. So it's a yes. And it includes both, okay. Even though when we say yes, we should should do DFS clear on parent of best. What is best? Well, best is 2. Well, technically 1 when we 0 index. And so, what does that mean? So, DFS clear parent best. And best is not 0 and included. Clearing 0 from 1. Right, okay. And that should, when we do DFS clear, current tree void for the next, if next is previous, right, we continue. If not included, included next is false. Oh, but we didn't incur, right, okay. Is that what the problem was? So, actually, we should just do that here. So we say yes, clearing parents, false, true. There's only one node, current root is 1. Yes, okay, that's good. So let's say, okay. Let's say we do 1, 2, 3, 4, 5, 6. So there's one test. 6 nodes. 1, 2, 1, 3, 3, 6. It should query 2. And let's say that it's like so it has about, okay, let's say that it's here. Let's say it was here. Oh, we didn't do the leaf trimming thing, but I doubt it's gonna make a difference. So it asks about 2, and we'll say no. So true, false, false, true. Assuming we haven't trimmed the leaf, then yeah, that's good. And so what we can do then is, okay, so we only have 3 candidates, and so it's gonna ask about 6. We've moved up from 6 to 3. So we're gonna say that no. About 3, and we say now it has to be 1. Okay, that might actually be it. What's this example they gave? They gave one. also goes to 4. 4 goes to 5. Also it's like a chain here. Okay. And what, for the second case, the node is in node 6. Okay. So let's say that that's the case. Then I'm gonna ask about about 4. And yes, we'll say it's in there. And so false, false, false. Yes, okay, wow, got it correct. Okay. And then it asks about 6. And because we answered correctly, it didn't move up, so it's still there. And oh wow, yes, okay. Nice, okay. I'm gonna try it without adding the leaf trimming stuff and just see if it works like that. It might actually. Hopefully all the queries are well formed. Just like error on test 1 or something. Dude, I'm stressing. Oh man, okay. asks about, let's assume that it's on 3, and so it asks about 2, and we say no. So it's jumped up to 1. So it could be yes and yes. We say that it's not there. And it's really, okay. So we say that it's not on 3. What does that mean? So it means that current root is not 0. So we say no. What does that mean? So we do a DFS clear on, that's about 3. Root is not 0, well it is 0, including parent. Right. Normally that would re-add the parent, but I see, okay. That should only happen if we're not equals 0 and maker's not 0. Because it's trying to trim the leaf, but it's like, doesn't really make sense here if it's the root. So what else about 2? No, no, it has to be 1. Okay. We'll actually just add an assert. Like, Oh, 6. Okay. Okay, so that was the issue before. It was that we weren't trimming the leaves. Oh,
and I guess that means that even though we're re-adding the root, since we're always trimming at least one leaf, the number of nodes never grows if we're wrong. Which is what we want. So then it's literally getting cut in half every time. And maybe it becomes, you know, the seal of, like the ceiling event over 2, but that's it. Otherwise, yeah, you could probably have cases where you're just constantly re-adding nodes at the same rate that you're removing them. Or at least it's catching up at a rate that within 160 queries you're not going to be able to do it. Nah, I just gotta wait, I guess. And I probably shouldn't submit E2 until E1 is graded. But if E1 works, E2 should probably work. It's just the same thing. But how many pre-tests will it be? That's the real question. In the meantime, I'll look at my problem path. I'm definitely not going to get it, but I just want to read it. Polygonal segment. Oh, okay. So the max is not greater than or equal to the sum of the remaining elements. Yeah, this is like that LeetCode problem. Yeah, find polygon with largest parameter. Where it's pretty much greedy, and you just consider all of the... Oh, that's it! You consider all of the possible maximum values, and when you have that, there's only a logarithmic number of other values it could be. Yeah. Come on, this is so slow. As long as I can just get my E2 in before the time, then I'll be fine. But you have to answer queries for this, which makes it a data structure problem probably. If there is no polygonal segment, which is only going to happen if you have like 3 elements, and the third one is like way larger. Or, you know, they increasingly become larger and larger, which... You know what you could probably do? You could have like, in the same way that you compute like a maximum tree, you could have like, you know, a top 2 maximum tree, where you store the top 2. And in this case, because the number of candidates is log n, you could have like a top log n tree or something. It's kind of janky, but... Yeah, so you are doing range maximum queries, and if you were just using a regular maximum tree, how would you compute that? Like you compute the maximum somewhere, and you'd find the position where it was. Then you would check left and right of that, and so on. It's still going. You know what, I'm just gonna... Same submission for this, I'm gonna put it in the user. Unless it, yeah. Man, I feel like if I had more time, I might be able to do this one. In 8 seconds as well, okay. So... How many... Okay.
is 2e5, so is the number of queries is roughly the same. Large array values. But it's log of 10 to the 12, so what is that? Only 40 elements. Okay. Yeah, so you'd have to get the maximum, and then get the... Oh, it is running both, okay. So you have to get the sum of elements within the LR range. Then you have to get the maximum. And you have to make sure that the maximum minus the others is not... maximum minus the sum of the others is greater or is less than 0, really, because of the triangle rule. And assuming that you can't have like a polygon with area 0, like where you have like a triangle with side lengths 1, 1, and 2 or something. And so that query the largest. If that's not the case, then what's going to happen is that it's going to split it up into 2 segments, and you just ask the same thing 2 other times. And so the worst case is you have like a really large number that's greater than the sum of everything else. And then you have the left and right half, and each of those are like the same exact structure. So the largest value would be like, 10 to the 12. And then in one of the halves you have like, well, the sum has to be less. So it'd have to be like 10 to the 12, like a fourth of that. And then the other elements are a similar structure, but their sum is like slightly less, like 1 less or something. And so the number of times it can branch is equal to... How many times would it branch? I mean... It gets cut in 4 every time, but you have to do 2 queries. So, oh, it passed. Okay, nice. Man, 100 pre-tests. So, yeah, every time it branches off in 2, and the number of times it's going to branch is just log n. So 2 to the log n, so it's just n total queries, which is, we want each query to be faster than all of that, which is the problem.
Check it out. Yeah. Everything goes exactly as I predicted it. The minutia is different, I nailed the gist of it. Just failed to adjust, baby, it was a bust. As I was saying, Craven Blunt, step up and started playing. Somebody save us,
But you could probably compute something where it's like, for each number, if we consider it the maximum side length, we compute the largest polygon, or we compute the smallest polygon that's still valid. So basically figure out how far to the left you have to go to add values until it works. And then of course if you're querying a left-right range, you get the maximum, and then you look
at that number to the left, and you find out if it's in the LR range. If it's not, then you can't use that number, and so you could either pick the second largest value or something like that.
Probably not gonna do that one though. Realistically, I mean, 9 minutes. See the standings though. Dude, 41st place? That's actually really good. 41st, I mean.
Have you been here as well? It feels super
Not
familiar.
41.
Pray tell, ever get the urge to take a draft of Mimir as well? Trip on what's knitted within cashmere veil, Egyptian glyph, cavern sequence, in sleep magic dreams reveal hidden patterns.
And that's
Queen, what
before
is real
E2
and
actually,
imagined.
so.
Money I have a secret, spoiling ending. I wish I couldn't see it. To me, it's no more profounder than mere logic, a downer beyond years as we flounder and
Still gonna
flounder.
think
I
about
thought
this a
would
little
be
bit though. I
inescapable.
mean,
Like love lost, long-term users incapable of forming any action spontaneous.
another question is if you could do some sort of like Mohs algorithm thing, where we process the queries in a specific order, so that the ranges are always pretty close to each other. That could be another thing. And so we're basically just like expanding our range to the right and maybe shrinking a little bit to the left. And what that could mean is that, oh, but we have, no, we have updates in between, so that wouldn't be possible. And also, okay, I guess we don't, if we pick a maximum, we don't have to pick to the left or like specifically to the left. We can pick anywhere around it. So that's another useful thing. However, if the maximum isn't valid, you do have to pick a specific side, and that's the important part.
Spread love, feel the vibe, get buzzed. Spread.
I wonder if you could merge queries, like kind of treat it like a segment tree. If you have two segments that are both valid polygon segments, you can combine them into one segment that's also valid. And I mean, visually, you can just connect the two polygons. Not too bad. And so, based on that, although you could have invalid segments that become valid. And they would become valid if the maximum of the two segments plus okay, the maximum of the two segments is less than or equal to the sum of the two sums minus the maximum. And you could build a segment tree like that, and I think based on that you could instantly query whether or not a left-right range was valid or not. But then again, you have the branching thing, so you might have to do some sort of like binary search thing. Like I know at Coder's library they have like a find first occurrence thing, so that could be it. Let's go. Alright, past the 100 pre-test. I think that is as good as I'm gonna get. 28th place, that's crazy. Next to Grandmaster, that's insane. Yeah, I'm glad I recorded that. That's like probably one of the best contests I've done. Yeah, I'm probably gonna cut it here because I don't think I'm gonna solve any further. But